A binary search tree is a binary tree, as the name suggests, with vertices assigned keys, which will be used in the search, such that the key of a vertex is larger than the keys of the vertices in its left subtree and smaller than the keys of the vertices in the right subtree. Now, this is a structure that we use extensively in storing data so that when we find to retrieve a value, we can find it in a very efficient time. Because if you remember, we talked about binary search, and we said that the numbers has to be ordered for binary search to work. And this is one way to achieve that order, because if you just use an array, updating the sorted array is expensive, but using a binary search tree, it's also much more efficient. Now, I'm going to show you how to build a binary search tree from key values, and this will be from scratch building a binary search tree, and then I will also show you how to search in a binary search tree. Now, suppose that these numbers are going to be stored in your binary search tree, and then you'll use it to search the items in this list. The first value you have is 7, so that will be the root. Okay, you select the first one as the root, and then comes 12. Now recall the definition. The key of a vertex is larger than the keys of the vertices in its left subtree. So the key of 7 is going to be larger than all the key values in its left subtree. Because it's a binary tree, you just have a left subtree and the right subtree. You don't have a third one. Therefore, you cannot put 12 here. So you have to put 12 in the right subtree. Therefore, you add it as a child of 7, but at the right-hand side. The next value you get is 4. Now, again, recall the definition. Due to that definition, 4 has to be in the left subtree. Therefore, you'll have to put it as a child of the root 7 on the left-hand side, because you have to put it in the left subtree, and this is the first position available. The next value is 1. Now you see the root has 2 children, and this is a binary tree, so I cannot add it like this, because it will be the third child of the root. So I will have to, well, 1 is smaller than root, so it has to go into the left subtree, but it cannot be a child of the root, because the root already has 2 children. So it has to go as a child of 4. And since 1 is less than 4, it has to go to the left subtree. The next item is 9, and it has to go to the right subtree of the root, because 9 is greater than 7. But again, since 7, the root already has 2 children, 9 cannot be added as a child of the root. So it has to be a child of 12. Since 9 is less than 12, it has to go to the left subtree of 12. And you continue like this. 8 is the next value. And since it's greater than the root, it has to go to the right subtree. And then you compare it with 12, and it is less than 12. But you cannot go like this, because the left child of 12 is already occupied with 9. So you have to go one more step. You have to go like this, because 8 is already also less than 9. Next, you get 16. Compare it with the root. 16 is larger, so it has to be in the right subtree. Then you look at the root of the right subtree, that is 12. 16 is greater than 12, so it has to go in the right subtree, so you place it here. Next is 11. From 7, you have to go to right. From 12, you have to go to left. From 9, you have to go to right. So put it here. And then finally, you add 5. With 7, you have to go left. With 4, you have to go right. So you place it here. Now, when you build this search tree, it's easy to search here because, for instance, if you are looking for 11, you first check the root. Since 11 is larger than 7, you see, look at the right subtree. Every vertex, the key value is larger than the key value of the root. And here, every key value in the left subtree is smaller than the key value of the root. So since 11 is larger than 7, you know that it can't be here. So you eliminate half of the structure in one iteration, in one comparison. Then you just look here. Now the root is 12. So this is a recursive algorithm in that sense. You just now searching in this subtree. The root is 12 and 11 is smaller than that. Therefore, I need to check this part, and this part is eliminated. Now the root is 9. Okay. Therefore, since 11 is greater than 9, I have to search it in the right subtree, which, since the root has 11, I have found the key value. Now, if you cannot find the value in a leaf, that means it doesn't exist in your binary search tree. So this is how you search using binary search algorithm on a binary search tree.